Hello everyone, welcome to today's talk. Today we have Chun-Sheng from Humboldt-University of Berlin, who recently completed his PhD in low-dimensional topology. His work is mainly about classification of some different type of knots and so on. And we invited him to give a talk on fundamentals of knot theory and introduce the subject to our audience. And so thank you, Chongqing, for coming, and you're free to speak.
Okay, yeah, thank you for the introduction and also for the invitation. Um, yeah, so I'm Chun-Sheng and I am a PhD student in Berlin, just about to finish. And yeah, originally I'm from Taiwan actually. Um, okay, yeah, so I'm going to yeah, give a very brief overview of to the introduction to the topic of knot theory. And well, actually, I work more in the yeah, and as Shah said, in the low dimensional topology. So that also involves three manifolds, four manifolds, and also knots and surfaces embedded in such objects. Okay, so let's start with what I'm supposed to talk about. So what are knots? So knots are embeddings of one-dimensional spheres. So a circle is a one-dimensional sphere embedded in three-dimensional space. So usually we start by talking about embeddings of S1s in S3 in the three-dimensional sphere. And we talk about such embeddings up to isotope. So what you can picture in your head is we have this knotted S1 in free space, and you're allowed to push it around. So you're allowed to push it around without cutting it or without pushing strands of itself through itself. That's forbidden. So if you do that, you would be considering a different knot. Yeah, so more technically, up to isotopy means so if two knots there we consider them as equivalent, meaning there exists a smooth isotopy between the two embeddings. So you have a one parameter family of smooth embeddings such that at the beginning, so at time one, you it gives you the embedding of the first embedding, and then at time one, it gives you the other embedding. So a priori, they could look very different. So we'll come to that in a second. And the the sibling of knots are links. So links are the case where you have more than one component of S1 embedded. So for example, in this picture, this is maybe the simplest example of a link where you have two components and each component is just something that we call an unlink, unknot. So it consists of two of the easiest knots, if you like. So the unknot is a embedding into S3, the three-dimensional sphere, such that it's actually the boundary of an embedded disk. Okay. But I think throughout this talk, we will mainly be talking about knots. So the special case where you have just one component. Okay. And these pictures that I've shown you they're supposed to represent these three-dimensional objects. So knots, they're one-dimensional, but they are embedded in a three-dimensional space. And we, it's common to depict knots or links in something called knot diagrams or link diagrams. And so what are link diagrams? Um, so they are kind of a specific chosen projection onto the plane or onto the paper or blackboard, such that you only have so the pre-image of every point is at most 2. So you only see, for example, here where there are 2 strands lying on top of each other. This is something that we call a crossing. And you don't want to have 3 strands meeting at a crossing. You at most allow 2 of them. And for any embedding of an S1, so for any knot, you can always find, after suitable isotopy or perturbation, if you like, um, to find a good projection where you only have where you only see 2 strands at most meeting at a crossing. And the way we draw them to indicate which one is on top from your viewpoint is simply you draw it connected, and the one that is below it you draw it with a little break in between. So the knot is not broken, but it's just to indicate that it's lying underneath it. Um, okay, so once you have so one maybe obvious thing is that you have infinitely many ways of projecting um, an embedded S1 in free space to a plane. You have infinitely many such choices. Um, and so Reidemeister's theorem tells you that um, for 2 different projections of the same knot, you can go between them by these 3 kinds of moves on the plane. So now we're talking about um, diagrams of the knot. And so, for example, wherever you see such a crossing, you can just pull it straight. It's clear that this can be realized by an isotopy, so it doesn't change the underlying knot type. Or if we look at the second type of move, when you have 2 strands that are parallel, it's fine if you just pull one over the other one to create 2 new crossings, or undoing this, so to undo 2 crossings, that doesn't change the knot type. So what Reidemeister's theorem tells you is that for any 2 diagrams of the same knot, if you do these moves, you will not change the knot type in particular. And so if we started with a very simple diagram, for example, the one here, you're allowed to do these moves to make it to get a very complicated diagram of the same knot. Um, okay, so now we want to come to the first invariant of a knot or links. So the question is asking, so how complicated is a knot? So one very simple um, way to to encode this the complexity of a knot is simply you count the number of intersections in your diagram. But what Reidemeister's theorem told you is that you have infinitely many diagrams. So how can you for the same knot, you have many different diagrams, and they certainly can have many different contain many different crossings. So to get an invariant for the knot, and you want to take minimal over all diagrams of the knot. So the crossing number of a knot is going to be defined by the minimal number of crossings among all the diagrams of that knot. So this is easy to define, but can be very hard to calculate because you have to consider minimal over all diagrams. And so now here we come back to the simplest knot in terms of this complexity that I just defined in terms of crossing number. So this is the knot with the least crossing number possible, except for the on knot. So the on knot is the only knot where you have a diagram with 0 crossings. So the crossing number of the on knot is 0. So in particular, it's 0 if and only if it's the on knot. And here we have this is a special diagram for the trefoil. It's because it's the one where it contains the minimal number of crossings. So I'm claiming that the crossing number of the trefoil, it's the name of this knot, is in fact 3. You cannot do better. Um, okay, so now I'm going to shift the thinking a little bit. So we talked about isotopy, moving the knot in space, and that also kind of corresponds to Reidemeister moves, so changing the diagram but without changing the knot type. So another question you can ask, how complicated is the knot? Is so how different is it from the on knot, for example? And so now we're going to again consider the trefoil, and we're going to do something that is kind of forbidden. So we're going to so what happened from the left to the right is if you look at this crossing, we changed it. So what that means is we moved what was the lower strand through itself to become the upper strand. So that changed the knot type. Um, so here the question is, so in particular, um, I want to explain to you now that crossing change, so changing from this picture in the diagram to this picture in the diagram, is an unknotting operation. What does unknotting operation mean? It means that after doing it finitely many times, moving the knot part two strands of them through itself to get a new knot, that you can eventually end up with the unknot. So if some operation allows you to reach the unknot, then it's an unknotting operation. So let me explain now why crossing change is an unknotting operation. So, so here's the first example of the trefoil. Um, the claim is that doing one crossing change is enough to go to the unknot. So if we okay, so here to here, this is the crossing that we changed. And how do you see that now this new knot is actually the unknot? So we do Reidemeister moves because here we have a diagram and you see that, okay, this strand is lying completely on top of the strand. So we can just pull it over. And then there's this crossing that you can actually just unflip, just flip this arc. And then you end up after these two Reidemeister moves or isotopy, you get a diagram of the unknot. So these two knots are actually both diagrams of the unknot. And in general, when you have a diagram, just imagine when you follow along the knot diagram, you want to be let's say in this picture we have three crossings. If you start walking along the knot, you're going to pass by the three crossings. Each crossing you're going to visit twice because there are two strands meeting at a crossing. So you're going to be walking by six crossings in this case when you walk around the trefoil. And you want to be always, let's say, going on top when you walk along the the diagram. For example, if I start here, I'm on top, on top, on top. So I've been on top three times. That means the rest is going to be under. And that means you have achieved um, being an unknot because if you imagine your unknot as a like a rubber band, you hold it in free space, and choosing a projection would be like putting it down on the table. And when you do this process slowly, some knots, some part of the knot are going to touch the table first. And when you essentially lie it down slowly, the first parts that touch the table, they're going to be the under strands, and then the parts that reach the table later, they're going to be on top. So if I have my crossings distributed in this order, that means I can undo it, like I can just take it up and I will get an unknot. So um, so this is also supposed to prove the following theorem, that the unknotting number, okay, so I haven't defined it, it's the minimal number of times you need your knot to cross itself to go to become the unknot. So in particular, um, I hope it's now clear that the unknotting number is bounded above by its crossing number. Because if you have here this diagram, or we already know, or I claimed that the crossing number for the trefoil is 3, and the unknotting number for the trefoil is 1. You only needed to do one crossing change. But you need at most three. So because in this diagram, there's three crossings. You just need to make choices at each of the crossing. Which one should be on top, which one should be below to give you the on knot at the end. So that's why, or another way to read this would be the unknotting number is a lower bound for your crossing number. In general, for such invariants where you define it by taking a minimal, it's usually more difficult to find a lower bound because to give an upper bound, you just give an example. For example, if I want an upper bound for the crossing number of a knot, I just draw a diagram. And then that would be, I don't know if it's minimal, but that would certainly be an upper bound. Okay. So now I'm going to talk about um, a, a very classical conjecture about unknotting number of knots. So here we have an operation given two knots, how you can build a third knot out of it. And this is something called connected sum. So there are some technical details or of how this operation is well defined, but I'm not going in that. But um, I think the picture is quite clear. Like here you take, in this case, I have two of the same knot, both again the trefoil. I pick a little ball around it where it intersects my knot in a very trivial arc. I'd pick two such balls and then I merge them by saying, okay, this endpoint enters the other knot from here and it runs around here and then goes from here to here. So this is my new knot. This is called connected sum. And so very old conjecture is the unknotting number additive under the connected sum. So particular, if I have two knots, K1 and K2, is the unknotting number of the sum of these two knots the sum of their unknotting numbers? And this was has been open for a very long time until last year. So not
Oh,
until
sorry.
last year.
So
Sorry.
the connected sum operation is allowed to be performed anywhere on the knot.
So
Doesn't depend on the place you.
yes, so actually it's defined for oriented knots. So once you have an orientation, then it's well defined and it does not depend on where I pick that little ball. Yes. Okay. Yeah. So please, if anyone has any questions, please feel free to ask, interrupt me. Um, yeah. So the name of the paper is very summarizes the result. So it tells the paper is called Unknotting Numbers Not Additive under the Connected Sum. And so what they found is, um, or one example that they found is you have two knots, both have unknotting number 3, and once you take the connected sum, they show that the unknotting number of the new knot is less than 6. But what is still open is that they don't know the unknotting number of that knot. They just are capable of showing that it's less than 6. So it's less than the individual parts of the summons. Yeah, but I don't plan on going more into detail in this direction, but I
So
invite you
if I
to
need
look
to,
this paper up. Yeah.
okay, so it's going to be a very exotic example. But okay, how they prove this thing exists? Is it some kind of abstract theorem saying that just this not exists with this property, or they really constructed
It's
geometrically?
very concrete examples. So they give you the knots, they give you the pictures, and they say, okay, move this strand here, and then you get the unknot within
Yeah,
with less than 6 steps.
interesting. Okay.
Yeah, so they show you can unknot it with less than six unknotting crossing changes, and but they don't know whether that's optimal yet. And there are still many open questions regarding this. For example, um, we don't know if there are examples where you start with, let's say, and two knots where they are both on ending number 2 or 1, whether you can, in those cases, still reduce your unknotting number. So there's still it's still quite mysterious about this unknotting number. And it's people are interested on one hand because this operation is known for so long and it's very, yeah, very easy to define. Okay, and I'm just also going to briefly mention another conjecture, which is also related to unknotting. Um, so let's go back to crossing change for a moment. So here, whenever you see two parallel strands, you can do Reidemeister moves. I just pull the lower strand over the upper one, or you could also do the opposite one. It doesn't change the knot type. But now if I do this crossing change, so I think in this picture I changed this crossing, potentially this changed the knot type. And so what I'm just saying is that crossing change, you can you can view it as having two parallel strands, and then you add these. We call this a full twist, or adding two crossings. So this is the same as crossing change, but reformulated in this context, it's called a two move. So you have two parallel strands, and you add two crossings, or you add a full twist. Like they were running parallel, now you add a full twist. So a very similar move would be a four move. So you, instead of just adding one full twist, you now add two full twists or adding four crossings in a row. So this is called a four move. And similarly, you can define six move, eight move, whatever you like. And it's known that for six move or higher, they are not unknotting operations. So you can have a knot, and no matter how many times you do six moves, you will never be able to reach the unknot. So it's not an unknotting operation. But so it's what is still open is whether the four move is an unknotting operation. So we do not know if for every knot you do enough finitely many four moves, you will be able to reach the unknot. So this is still open. So there are some, for some families of knots where this is true, where this is an unknotting operation, but in general, we don't know. And there's also perhaps not strong evidence why this should be true, but somehow this is the middle case where four move, we still don't know. Okay, so now I'm starting to move away from crossing number or this unknotting operations. We're going to move up in one dimension. So we're talking about knots. These are, if you have heard of the word manifolds, these are one-dimensional manifolds or just one-dimensional geometrical objects. Now surfaces come into the game. So um, so what is a ciphered surface? So the term here in italic, what is a ciphered surface for a knot? It's simply a compact and oriented surface such that the boundary is your given knot. So the ciphered surface for the unknot are as shown. For example, here you can have as many holes as you like. These are all ciphered surfaces for the unknot because the boundary of the surface is here drawn in this. I hope it's a little thicker, this unknot. So, or in particular, if the genus is zero, so if you don't have any holes, it's just the disk. The disk would be the simplest ciphered surface for the unknot. Okay. And so also as this example shows you already for the unknot, you have infinitely many ciphered surfaces because you can just add as many holes to this surface as you like. Um, okay, and what about other knots? So the unknot has infinitely many ciphered surfaces. What about other knots in the three sphere? And so now I'm going to give you a proof that in fact every knot or even every link in the three sphere has a ciphered surface. So meaning there exists embedded, compact, oriented, connected surface with that given knot as boundary. So here, this is,
Sorry. Okay.
yeah.
I think maybe I confused something. Um, So the minimal genus
Yes,
is constrained, but you
yes,
say you can add more genus.
exactly. Exactly. We will come to this point. So,
But wouldn't that
uh,
change some kind of, if you add like more genus to the surface, wouldn't it change the self-linking number of the knot?
um, so I mean, the knot itself is lying on the boundary of the surface, or it's not lying on the surface. So I'm not sure what you mean with self-linking number in
I,
this
I
case.
thought I thought this genus is some kind of invariant to the
It
knot.
is. It is. I will define an invariant for
Okay.
knots using separate surfaces. Okay, and since you gave it away, I can say it now. It's going to
Sorry.
be what is the minimal genus of a Seifert surface for that knot. So that gives you an invariant for that knot. Yeah. Okay. Uh, so yeah, that's what's going to happen in I think 4 or 5 slides. Okay. But yeah, but in order to define that invariant, we have to show that okay, every knot has at least one Seifert surface, right? So that you can take minimal. Or okay, so now I'm going to present what is known as Seifert's algorithm. And maybe this is why we call these surfaces Seifert's surface. So we're going to pick an orientation on our knot, and an orientation is simply just a choice of which way we want to go around the knot. And when you have a link, you choose it on every component. That would be an orientation for your link. Okay, and next step, we want to resolve the crossings. So I want to end up with a bunch of circles. And how I change the crossing just depends on the orientation. So in this crossing, for example, I come in here along my orientation. I want to leave on this side. So this is what we mean with resolving a crossing. So you do this at every crossing. So for example, here the orientation goes in like this, and then I follow the orientation of the other strand out. So I get a circle here. So after doing this, I will end up with potentially nested circles, which we call Seifert's circles. And now you want to interpret these circles as disks, actually. So in this case, I have 3 disks. They're disjoint. You can imagine they're embedded in R3 at different heights. So this little circle is above the bigger circle, the bigger disk. And this is something not connected. And well, the boundary right now is just 3 unknots. It's not the knot we started with. So what we do now is we add some bands. So what is a half-twisted band? So imagine you have a rectangle and I rotate one end. So this is what I mean with a half-twisted band. So when you rotate half half a twist, you see this crossing from the side, and wherever I had my crossings, I will attach a band. So in this case, I started with a diagram with 4 crossings. So I attach 4 half-twisted bands, and now I get a compact surface, and it's also orientable. That one can check. And one can also check that the boundary of this surface is precisely the knot you started with. So this proves that you give me a diagram of your knot. I can build you a Seifert surface for it like this. And
I'm
what
sorry.
is, yeah,
Can you repeat how do you then construct this surface? And is
okay,
it
yeah,
the minimal one?
very good question. Okay, so let me just repeat. So um, we start with a diagram. We give it, you can choose any orientation, and we do this smoothing operation. So whenever you look at a crossing, you look at how you walk along the orientation. So you either let this connect to this side or this side. But if I go this side, I'm going against the orientation. So that I don't want that. So I want to go this way. And you do this at every crossing. For example, here, I go down. I don't turn left. I don't go this way because that would be against my orientation. So I go this way. So I get here these circles. And now I interpret my circles as the boundary of disks. So so now I see three different disks. And you can imagine that they're not intersecting each other, that they're on different heights. So without loss of generality, the smaller one is just lying above the disk below. And now I attach bands. So these are rectangles, and they have these two sides where I'm going to attach to the disk. So I have a disk. I'm going to glue the two parallel edges of the rectangle to the disk to form a new surface. And the band is such that there's a half twist. So not a full twist would be doing a 2 pi rotation, but just a pi rotation on the side. So that's what I mean with half twist. And where do I put them? I put them exactly where my crossings used to be. And also, one should ask, okay, to do a half twist, you have two directions, right? You have a pi or a negative pi. And how do you choose that? You choose it according to the kind of crossing you had. So, um, so if the crossing was twisting in this direction, in this case, this is something called a positive, just for convention, positive crossing, then you would add a positive twist. And if it's a negative crossing, you add a negative twist. And so this end surface consists of 3 disks and 4 bands connecting them. So this is now something connected and compact. And the fact that it's orientable has to do with that you had an orientation and you glued them together. Okay, so what this is showing you is that, okay, every knot or every link has a Seifert surface because I just built you one. Okay, and so you can try to calculate the genus of the surface. And it turns out that if you started with a different diagram of the same knot, you can get um, a different Seifert surface. You can get a different Seifert surface, different meaning, for example, they have different genus. So a good question is, so how do you get the minimal genus one? So we will come to this. Okay, so now we can okay, so
Um,
first,
I'm
yeah.
sorry. So the surface you constructed gives a positive orientation to the knot, the one you chose already
Yes,
by construction.
yes, there is the surface induces an orientation on a boundary
It is
and
the
you
same
want
as
it
you, the
to,
one you started with.
yes, yeah, yeah. Okay. And so a Seifert surface for a knot is, we call it canonical if it can be constructed using this algorithm that I just described you, using Seifert's algorithm. It's called canonical Seifert surface. And so here's a invariant that Shah has already foreseen. So the canonical genus of a knot is the minimal genus of all the canonical Seifert surfaces for that knot. Right? Because I told you that if you start with different diagrams of the knot and you apply Seifert's algorithm, you could end up with different genus Seifert surfaces. So we take the minimal genus of all these canonical Seifert surfaces, and that gives you the canonical genus. Okay, and one could also ask, why do I need is the adjective canonical actually redundant or not? So one can just similarly define the genus to be the minimal genus of all Seifert surfaces. So, um, so the question is, okay, so are these two notions the same or not? And I would say it's very surprising that actually these two notions are different. So what does that mean? It means um, there are Seifert surfaces that cannot be obtained using Seifert's algorithm. And this is what I want to sketch a proof for you. So the fact that these two invariants, the genus and the canonical genus, are strictly different. So a priori, by definition, it's clear that genus is going to be a lower bound because you're taking minimal over all Seifert surfaces. There's no constraint asking, oh, the Seifert surface has to be canonical or not. So what is surprising to me is that there are knots where this is a strict inequality. Okay, so I already told you that there exist such knots, and this reference is to a related topic. Today I don't plan on talking to you about free genus, but that's again some other genus, and it's also very interesting. Okay. Um, Yeah, so as a corollary, this of the fact that you have for some nuts this um, it's not equality. It means that just to repeat that there are some Seifert surfaces that cannot be obtained via Seifert's algorithm. So that means you take any diagram, you will never get the minimal genus one by doing Seifert's algorithm.
And different diagrams might lead you to a different genus.
Yes, exactly. And but you might never get the minimal genus one.
Even from the minimal one.
Yeah, even from the minimal diagram. So yeah, there is no diagram where you find the minimal Seifert genus Seifert surface. And so now, so the title of my talk was knots. We have been talking a lot about them, and now this is where the polynomials come in. So this is really just one among many, many applications of polynomials invariants defined for knots. Um, so here I'm going to talk about something called the Homfly polynomial. I- Can you actually see it, or is the toolbar blocking it? Because for me, it's blocked. Okay. Um, so the Homefly stands for the authors of their discoverer. There are two independent groups, so it's called the Homefly PT polynomial. And so it's a it's a link invariant for oriented links, and it appears as a polynomial in two variables. It's a Warrant polynomial, and it's characterized by the two properties. So the first one is kind of something you want to ask for, you like. So for the unknot, it should be the trivial polynomial in some sense. So it's just one. And um, so here it involves a little bit of explanation. So what do I mean with PK plus? What is also interesting is that it can be defined from a diagram. You start with a diagram of your link and you pick a crossing. So let's say this crossing, and you look at the diagram. It's a new diagram, could be of a different knot, where you changed one crossing. And so you have, in particular, these are just one crossing of a given diagram. And if I change this locally to this one or this one, now I have three diagrams where they all just differ at this one crossing. And we have these three versions. So we call them the plus, the minus, and the zero diagram. And um, the polynomial that you associate with these three diagrams are going to be related by this relation. So the polynomial that you relate to the diagram where you have one crossing like this, and it's related to the polynomial where you changed one crossing in the diagram, and also to this one where you resolved the crossing. Okay, so this is called the Skine relation. So this is so what is difficult about this theorem is that you show that it doesn't depend on the diagram. so that it's actually an invariant for the link. Okay, and this is a very powerful invariant. It generalizes um, previously known um, polynom polynomial invariants for links, such as the Jones polynomial. Also, it also generalizes the Alexander polynomial. So what I mean with generalize is that you can retrieve these by substituting in some variables. So it contains strictly more information. For example, um, what the previous for Alexander polynomial couldn't distinguish knots up to their mirrors. So sometimes the mirror image of a knot is not the same knot again. But this is something that Alexander polynomial couldn't distinguish, but the Jones polynomial was able to. And now the Humphrey polynomial generalizes both of these.
I'm
Okay.
sorry.
Yeah.
I think I just didn't get it. If I give you a link, then which you say L, then
Yes.
you gave it a Laurent polynomial,
Yes.
which has the property that it's equal to one if it is an unknot. So it's just one component.
Yes.
How do you then construct for any L?
So you would be breaking the picture down. So
Mhm.
you would be reducing the diagram steadily. And you end up at the end, you'll be collecting lots of these variables until you reach a bunch of unknots. Because for the unknot, you know that the polynomial assigns to
Uh-huh.
it
Right.
one. So you
Okay.
start with a diagram, and then you gradually change the diagrams to the unknot. Since we already know that doing these crossing changes, you will end up with the unlink. Yeah, um, so this would be, yeah, one way to calculate examples by hand. But now there are also computer softwares where they can do these calculations for you.
Okay. Okay.
So,
Thank you.
okay, yeah. Okay, and this is just one application of this Humboldt polynomial. So with this thing, degree to max z of the phi pt polynomial. I'm just denoting the maximal degree, the maximal power of the z um, variable. So what Morton showed is that this maximal power is actually a lower bound for twice the canonical genus of a link. So um, so we can now consider this example. Um, So this is called the Chun-Sheng cable of the trefoil, and um, I mean it is reminiscent of the trefoil, right? You have this pattern of the trefoil lying there, and the Chun-Sheng is cable is just some construction to build more complicated knots. We will not go into this today, but what is known, it's especially for you have formula for calculating the genus of knots for cables. So we know that the genus of this knot is two. And using, so I didn't calculate this myself, but I used a math program called Sage Math to give me this Humfly polynomial, Humfly PT polynomial. And then I look at the highest coefficient of the z variable, it's 6. So by the previous Morton's inequality, I get this lower bound. So I get this lower bound of 3, so that in particular it's strictly greater than 2. So um, so here using Morton's inequality, we can deduce that this is an example where it doesn't matter which diagram you pick for this knot and you apply Seifert's algorithm, you will never get the minimal genus Seifert surface. Um, okay. So, so now I'm going to again add more things to more dimensions to my talk. Now we're going to um, look at families of Seifert surfaces. So in particular, if I have a family of Seifert surfaces, they're going to be filling up a three-dimensional space. So now um, I'm going to introduce a new definition. So a Seifert surface, so let's say in three-dimensional sphere, it doesn't have to be, but for this talk, we're just considering this case. We say it's a fiber surface if it's the interior of a fiber, um, of a locally trivial fiber bundle. Um, so it's a map from S3 with the knot on the boundary of this Seifert surface removed, and you have a fibration over S1. So, or I could say, if this is a Seifert surface for a knot K, then the knot complement, so outside of the knot, you have a fibration over S1. So that means you're filling up the whole space, um, except so away from your knot, you're filling up the whole space with a one parameter family of Seifert surfaces. So this kind of Seifert surface is special because it can fill up the whole space, and we call it a fiber surface. So the most simplest example of a fiber surface would be the disk. And because now if we consider S3 with the boundary of the disk, which is just the unknot, um, you have an S1 family of disks filling up the whole space. So how do you see that? So let me draw a picture. So I'm going to draw my um, imagine S3 as being R3 plus the point at infinity. So now I'm drawing the z-axis in my R3. And so I'm thinking of this plus the point at infinity. So this is going to be my unknot. So that means if I go to negative infinity, I will go to infinity and then come back from positive infinity. So in particular, this is my unknot, or it's the boundary of a disk. So where do I see my disk? Um, so if I look at a half plane with the boundary of the disk, um, so this is supposed to mean dots, and I go to infinity. So this half plane is actually a disk. I think I'm writing outside the. Okay, so this is actually a disk with the boundary given by the z-axis plus the point at infinity. And you can rotate around the z-axis. So this is where you see your S1 family of disks filling up my whole space, my whole S3. So in particular, the disk is a fiber surface, and the unknot, so the boundary of the disk, we call it a a fibered link. Okay.
So there was an open book.
Exactly.
I mean,
So
in the
let me,
picture, I
yeah,
mean,
maybe I should explain this picture. So each of as Shah already mentioned the name, we call the structure also an open book.
I
And
just saw
each,
the picture. It was an open book hanging.
yes, this was actually a picture taken in a cafe in Barcelona. Okay. And each page of the book is one of these fiber surfaces. So you have this um, S1 family of of fiber surfaces. And the reason it's also called an open book because you have to open your book completely to get this S1 family. And so where is your link or not? It's the precisely given by the boundary of the binding of a book. So you have to imagine, for
Um,
example,
so
this
there is
part.
this,
Yeah.
sorry, there is this circular wire inside. There's
Yes.
a one in the definition.
Yes, exactly. I
Okay.
never noticed, but that's a very good observation. Yes. Yeah, so these special ciphered surfaces, which are called fiber surfaces, they fill up your whole space, um, and they all meet along their common boundary, which is the binding of the book. So um, okay, so this leads to our definition. It's just a link is called fibered if it's the boundary of a fibered surface. And I will not go into the orientation technical things. So what time is it? Okay. So I should wrap up. I think
Sorry,
I'm
one question.
yes,
For a given, let's say, not, um, can you find these vibrations or is one with different genus of the pages for the same binding?
very good question. Uh, okay, so this theorem should at least answer your question, part of your question. So Seifert surfaces are not unique. We know that you can have if you have it of genus K, you can have it of higher genus as well. But for when is a Seifert surface a fibered surface, if and only if it is the genus minimizing one. So this also points out that um, the genus minimizing Seifert surfaces are particularly interesting, at least if you care about fibered links. So the you cannot, and also the last part of the statement says that the the surfaces are unique up to isotopy. So if a link is fibered, it has a unique um, Seifert surface, also a unique genus Seifert surface that can do this filling up your whole space in this one S1 parameter family. So this was part of your question?
Okay, so once you find this vibration where it's one,
Yes.
then you are sure that the pages has minimal genus.
Yes, exactly.
This
Yes.
is crazy. I will tell you something later.
Okay. Yeah, and just a remark. So in general, there are uh, knots that have infinitely many different minimal genus Seifert surfaces. So the fact that this fiberness is very makes them very special to have a unique minimal genus Seifert surface. Um, okay, and just to finish off, I want to show you a animation. Um, okay, is that showing up? Okay, so this knot, can anyone recognize it? So I hope in this projection, this is the trefoil,
Yeah.
and it's showing you the fiber surface for the trefoil. So if I pause the video, you would see one fiber surface. And while it's running, it's showing you the whole family, the whole S1 family of them. And um, yeah, if you can,
So the self, wait, so what is the self-linking number? Is the genus of the minimal Seifert surface or
okay,
something related to
yeah,
that?
I think yes, yeah, I think that. So if you mean like a parallel push-off along
Yes, and then
uh,
it intersect the surface transversely.
uh,
Like if you put up
yeah,
the knot a little bit,
yes,
and then it becomes like transverse to the
yeah, yeah. So
surface.
you push it into the complement. Yes.
And okay, the self, so the intersection number is what? The
For
self
okay,
linking
so for the trefoil, the genus is one.
and the intersection number, the self
I think that's the intersection number two.
two, so some kind of
No, I mean one, like
uh,
TOO, not TWO.
okay.
Yes. Yeah. So. Yes. And yeah, so this video was not created by me, but I feel like sharing them. Um, so maybe I will post uh, the link of this website. So if anyone who wants to look at them later as well, there's also nice descriptions that you can read about. Mm, okay, I have to chat this. Okay, yeah. So there are more videos on it. I will let you have a look at them yourself. Okay, I will finish my talk here. Thank you.
Yeah, thank you very much, Chun-Sheng. It was an amazing talk. I mean, I learned quite a few things. So,
Yeah,
um,
yeah, I'm very glad.
yeah. So, if there are any question, please raise your hand or say it. Yes, watch it. Yeah.
Hi, hi, Chun-Sheng. Thank you
Hi.
very much, Chun-Sheng, for this excellent talk. Yeah, all of it was new to me, so
Okay.
please forgive my ignorance if I
Yeah,
ask
no,
this
no, this is
question.
very niche. Yeah, but of course, you can ask
Yeah,
any question you like.
yeah, and like all the way in the talk, I was wondering, like, because obviously the pictures are always helpful, and uh, uh, like mathematicians usually try to build some pictures to make things understandable. But I was wondering, what is the mathematical representation for for these like very complicated knots? Like how we represent them mathematically?
Yes, exactly. Like as I defined them, it's an embedding, right? But how do I tell you that embedding, and especially that I just care about the class of the isotopy class of the embedding? Well, I think there's a tons of answers to your question. So there's many ways you can encode a knot, a link, in a finite many amount of data. So um, there's many ways. So I mean, just like if you want to look up, for example, Gauss code, that's just a few numbers, and it defines you the knot up to isotopy. Or you also have okay, I mean, yes, the diagrams. I can give you a knot by drawing you a diagram. Um, what I personally work with is something called grid diagrams. And a grid diagram consists of a grid, and it's a bit like playing tic-tac-toe. You put X and O's inside the grid, and that will encode to you the knot. And if it's because it's just a set of um, X's and O's inside a grid, inside it could be an n times n grid. Um, so it's really equivalent also to just two sets of permutations. So there's really many ways you can encode your knot in a very small set of information. So in particular, these ways that I described, they're also very practical for giving a computer the information of a knot, because it's very difficult for the computer to um, yeah, to see something smooth. But of course, there are also softwares that do that. Like you draw the knot, and then it will convert it for example, one of these ways that is preferred by a computer to encode the knot. So um, yeah, so the answer
Yeah,
is there's many ways
yeah,
to do that. Yeah.
yeah, exactly. Because like when you were saying like showing theorems, I was thinking like where I would start with, like, like for example, the first one, I think its name was tripoil. So I thought, like, how
Yeah.
would I write it mathematically and then do something with it?
Yes. Yeah, but I mean, usually many theorems are like, let's say if it's for all knots, then you don't have to specify one
Uh,
knot. Yeah.
Okay, thank you.
Or yeah.
Yeah, and maybe like I couldn't catch exactly like the link invariant, like what was it exactly? Maybe I missed that.
Do you mean the linking
Like the notion
number
of
or
link invariant, like
okay? So I mean, link invariant is just an invariant of the link type. Um, so you give me a link, and then I associate to it some let's say algebraic structure. Can be a group, can be a integer, can be um, an exact sequence, or and that would be that's what I mean with the link invariant. So it shouldn't depend on the chosen diagram. It should only depend on the isotopy class of the link, right? So for example, if I look at a diagram, it has a fixed number of crossings. That's not a link invariant because if I change the diagram, if I choose a different diagram of the same link, it has a different crossing number. So it becomes a link invariant once I take minimal over all diagrams.
okay, great, thank you. And maybe one kind of a general question or rather stupid question. So like this word canonical, I saw the difference here, canonical and non-canonical. But
Yes.
like in our bachelor course, we would say like this is the canonical form, but we wouldn't know what is the non-canonical form or like what is that. So what is this canonical and non-canonical?
Okay.
In
So
general, like
yeah, so I mean, it's very canonical means different things in different settings. So we have this Saffold's algorithm, which is you give me a knot diagram, and then I build you a surface which has the boundary given by the knot you gave me, and a surface, a Seifert surface that is built by Saffold's algorithm. It's called canonical, and it's non-canonical if it cannot be built using Saffold's algorithm, starting with any diagram of the knot. So yeah, this is just the convention that canonical means it comes from this algorithm. And if it doesn't come from this algorithm, then it's non-canonical. And the genus canonical and non-canonical, or the canonical just means, yeah, it's also again related to Saffold's algorithm specifically.
I think my understanding is what it wanted some kind of general um, answer to,
I see.
like,
Uh,
yeah. So this like this term canonical or natural, they appear.
Yeah, I mean it's natural from the diagram. That's I guess yeah, like you give me a diagram, you can automatically interpret it as a surface. So now that you know Saffold's algorithm, when somebody gives you a knot diagram, they actually also gave you a surface. So it's more than just the knot type, but it's the a surface with a fixed genus given to you. So because it's not just any surface for that knot, but it's decided with that diagram given to you. So yeah, I don't think I can generalize it more.
yeah, thank you very much. I
Yeah.
think I would let someone else ask.
Okay. Thank you for your question.
Muhammad Awais, please go ahead. Awais.
Very much giving me a chance. I have one question about these fibered surfaces which appeared like at the cipher surface for a knot. So, what is the criterion on knot? Uh, so it seems like it's not possible to have fibered surface for any possible knot. So, is there any?
Exactly. Yeah, I should have mentioned this. So not all knots are fibered. Um, and uh, So, so one way you can obstruct whether a knot is fibered, or there's okay. So one characterization, um, there's something called a knot group, and the knot group is just the fundamental group of the knot complement. And if the knot group has has a finitely generated commutator subgroup, if and only if the knot is fibered. So this is somehow a very algebraic characterization. So
It means generated commutator, you said.
yes, so you consider the commutator subgroup of the fundamental group of the knot complement. So the knot complement is a three-dimensional space, and you consider its fundamental group. That's something that we call the knot group. And you want to look at the commutator subgroup of this knot group. And
Mm.
if this group is finitely generated, if and only if the knot you started with is fibered.
Uh-huh.
So this is one characterization. And
We have one knot like it's Z, so it is commutator is
yes, yeah, that
com-
would be
yes.
an intuition. Yes.
Okay. Well, that's a
Yeah.
cool.
Okay. And also, you can also read for there's something called an Alexander polynomial, which is a special case, if you like, of this Homfly PT polynomial. And so first of all, it's not a Laurent polynomial, it's a normal polynomial. And um, not every polynomial is realized as the Alexander polynomial or not. But if it is, and if the leading coefficient is one, so if it's monic,
Mm-hmm.
then there exists infinitely many fibered knots with this Alexander polynomial. And this is also a necessary condition. So if you have a Alexander polynomial of a fibered knot, it necessarily is monic.
Uh-huh.
So this is also, I'm also telling you that, okay, there are actually a lot of fibered knots.
Mm. And one more question I just want to
Yes.
ask. Like this complement is always a cyclic, like higher homotopies are always trivials.
Um,
Higher
you mean
homotopy.
of the, you mean of the knot complement or um,
I'm not
so
sure, like
that,
I
uh,
of
so you're asking because I talked about the fundamental group
yeah,
of
exactly.
knot complements. Um, I, I don't, I'm not sure, but
Because because then like there should be like a bunch of invariant for knots, no, like higher homotopy and so on. Like
um,
I don't know if it is. I have never seen somebody talking about that. Like
yeah.
that's why.
So what is most of the invariants are not complete invariants, meaning you can have two different knots with the same value. For example, you can have different knots with the same knot group, but the knot complement, this is a very big result that the knot complement is a complete knot invariant. So two different knots, they have homeomorphic knot complement if and only if it's the same knot. So you can't have two different knots with homeomorphic knot complements. So so sure, you can also look at the higher homotopic groups of the knot complement.
Mhm. Okay.
I feel like the knot complement is some kind of it's a homotopy type of this complement of this separate surface, some kind of. And so pi 2 might not vanish, but maybe the higher would vanish.
I think in general, I think they are also interesting variants.
Why they are the complement of cipher surface?
And I'm just saying that one may try to remove, so you take a surface with boundary on the knot and then remove the whole thing.
So that,
You get this complement uh,
yes. Yeah, the two-dimensional, so maybe it will not destroy
and
the.
then you can collapse the extra dimension to get something two-dimensional and then the higher homotopy. So it's seemingly some kind of genius,
Uh-huh.
yeah, some surface with boundary.
Okay.
Yeah.
Mhm. Thank you.
You're welcome.
Yeah, are there more questions?
Yeah. Yeah, so someone asked in the comments for suggestions of not theory books. I mean, there are many. I think there are many books called Not Theory or something like that. And there are like classical references would be a book by Rolfson. I'll type it and or Licorice. Yeah, but these books are classical, so also meaning old, and a more recent book, but it's not. It's a more has a specific topic. I think it's on hyperbolic knot theory in particular. That's a very new, a very recent book. But it has a particular flavor of knot theory, particularly from so considering those knots whose complements have hyperbolic structures, and so that would also be a book where it would lead you to quicker to current research. So I think one of the authors is Jessica Purcell. I'm not sure if they were, I forgot if there were other authors, but I think the book is called Hyperbolic Knot Theory or something like that. And yeah, so and also knot theory has recently become very closely related to not just three-dimensional geometry or also to four-dimensional topology. Um, I think there's a recent survey paper called A Not Theoretical Tour of Four-Dimensional Topology. So that would also give you a very different viewpoint of knot theory from because what I talked about is very just a tiny little bit of this theory. Yeah.
Perfect. If there are no questions, let's thank Chun-Sheng again. Thank you so much for this interesting talk, by the way. I think we really, and unfortunately today, by the way, the internet in Pakistan is, I think, is most of the area blocked because
Oh,
there are
really?
some
Okay.
religious activities happening, and most of our audience didn't come because
I
of the
see.
blockade.
Oh, okay.
But they will definitely watch your lecture. So
Okay. Yeah.
thank you again. Hope to
Well,
see
yeah.
you
Thank you
soon
too.
in Berlin, maybe.
Okay. Yeah. We'll keep in
Um,
touch.
yeah, thank you, Chun-Sheng and Shah. It was an excellent talk. So I'll just stop, hit recording, and maybe see you next time.
Okay. Yeah.
Thank
See
you.
you.
And by the way, good luck for your defense.